Welcome to this lesson about systems. What is a system? A system is any device which is doing an operation on signals. You have input signals entering the system, output signals exiting the system. For sake of simplicity, we are considering now a system that has only one input and one output. You have some examples of systems in the bottom of the slide. So the first one is like an amplificator. It multiplies the input by 3 times. The second one is computing the sinusoid of the input. A system is causal if the output follows the input in practice. So if the output at the time y of t depends on the input at the time before the time you are computing the output. The system is also said to be stable if, when the input is limited in amplitude, also the output is limited in amplitude. We are defining now a special kind of systems which are linear, and I will explain what does it mean linear here. So if you have the composition of two inputs, x1 and x2, and you have the output of these two inputs independently, the output when you put together in any linear combination x1 and x2 is the linear combination of the outputs you have before when you apply the input independently. So in this case, the system is linear. You have here some examples of systems. You can verify the linearity. So the first one is the amplificator. So it multiplies the input by 3. When you apply the input x1, you have 3 times x1. When you apply the input x2, you have 3 times x2. If you apply the composition of x1 and x2 for any value a1 and a2, you can distribute the 3 on the different terms, and you get that the output of the system, when you have the linear combination of the input, is the same linear combination of the output, so the system is linear. In the second case, you are computing the square root of the input, and this system is not linear because the square root of the sum is not the sum of the square roots. Another property that we are looking for is the time invariant property of the system. Time invariant means that the system behaves the same way all the time. So if you use the system yesterday or tomorrow, for the same input yesterday or tomorrow, you obtain the same output yesterday or tomorrow. How can we write this in a formula? If you have x of t in input and you get y of t, if you apply x of t minus tau, which is delayed version of x of t, you have the same delayed version of y of t, so y of t minus tau. If you put together the two properties, you say that the system is LTI, linear and time invariant. From now on, we consider the systems all LTY, and we define h of t, the output of the system when the input is an impulse. So h of t is by definition the impulse response of the system, which is linear and time invariant. Let's see what happens if we have a generic input x of t. So the output will be the gamma, which is representing the operation to do the system, applied to the signal x of t. We have seen in a previous lesson that you can decompose x of t like a summation of impulses, each one of these impulses in a different position, and each one of these impulses with a different area. And so you can replace the expression of x of t with this decomposition. The system is linear, so the integral is also linear. You can exchange the gamma with the integral. So instead of being gamma of the integral of gamma. So x of tau is like a constant, so the gamma finish in front of the only function that depends on t, which is the impulse. So you have the output of the system when the input is an impulse, and we already know this, is called impulse response. So every one of these terms, gamma applied to delta t minus tau, becomes h of t minus tau. And so you get that the output to any general input x of t can be computed if you know the impulse response and if you are able to do integrals. So if you put here in this integral the impulse response and the input that you already know, you can compute any output. This kind of operation, so the integral of this h of tau multiplied by x t minus tau in d tau, is called convolution integral. And so the output of a linear time invariant system is the convolution of the input and the impulse response of the system. You can see here what does it mean, this convolution integral. It means that you have the input made of many impulses. Each one of these impulses is producing an impulse response, so each one of these impulses is producing in the output one of these red lines. shifted because the impulse is in a different position. When you do the summation of all these red lines, you get the general output of the system. There is a movie trying to show this effect. It shows that when you have an impulse in the input and the impulse response is like an exponential function, you have the exponential produced by this, then you have the exponential produced by this other one, then the two impulses go closer one to the other, there is overlapping. Here you have many impulses and all of them are overlapping, and so you have a complicated output which is made by very simple outputs. So each one of them is an impulse response, but due to the overlapping they sum together. And this ends the lesson about systems.